In this video, I want to talk about how we can use our model, which we've estimated in factor analysis, in order to enable us to derive the model predictions of variances and covariances of indicator variables. So we've got this model up here whereby we have two underlying unobserved factors, measures of physical and mental health, and physical health loads on life expectancy and BMI, whereas mental health loads on how happy an individual feels and the degree to which they feel anxious. Furthermore, there is found to be a correlation between physical and mental health. And the numbers which I've drawn here are perhaps some sort of hypothetical numbers which we might get if we were to estimate this model on a sample. So remember from before, when we write our equation in stacked form, we have that the variance of y is equal to capital lambda, where lambda is our weighting matrix, where the weights of the corresponding factors on given indicators, times the variance covariance matrix of the factors, which I'm going to write here as capital phi, times lambda prime, our weight matrix, and then finally we have to add on the variance covariance matrix for our error terms, which are these numbers which you see up here. Okay, so first of all, how can we construct lambda, our weight matrix for how much the given factors load on the indicators? Well, because we've got four indicators, four observed variables, and we've got two underlying factors, lambda here is quite simply going to be a 4×2 matrix. So if we were to write it down, the first row would be representing this first indicator, life expectancy here. So first of all, if we think about this as being the first indicator and this being the first factor, so perhaps write this one as F1 and this one as Y1, then the first element is just going to be how much that first factor loads on the first indicator. So that's just going to be 0.6. And then we need to work out how much does this indicator receive some sort of weight from mental health. Well, there's no direct arrow joining these two, so the second element is just 0. Okay, what about the next row? Well, now we're talking about the next indicator variable, so BMI, and we want to know how much does BMI, first of all, load on physical, strictly how much does physical health load on BMI, and we can see that that's just going to be 0.9, and again there's no arrow joining BMI with mental health, so the next component is just going to be 0. Then what we do is we move on to how happy an individual feels. Firstly, how much does factor 1 load on happiness? Well, we can see here there's no arrow joining F1 with happiness, so that's just going to be 0. Then the next element is going to be 0.7 because mental health loads with a weighting of 0.7 on happiness. And then finally, we could do the same for anxiousness and we get 0, 0.8. So that's just our weight matrix. How about constructing this matrix phi, which is the variance covariance matrix for our factors? Well, this is easy enough. Because we've got two factors here, it's just going to be a 2×2 matrix, where the diagonals are going to be the variance of the given factors and the off-diagonal elements are going to be the covariance between the factors. So because we are talking about standardized variables in general, the diagonal components in this example are just going to be 1 because it's just going to be the correlation of physical and mental health, respectively, with themselves. How about the off-diagonal components? Well, we can see that our model here has predicted that the covariance between these two factors is 0.3. So the off-diagonal elements here are just going to be 0.3. So that's our variance covariance matrix for our factors. So what about constructing this final term, this variance covariance matrix for our errors? Well, it's relatively easy to do here because of the fact that I haven't specified any covariances between any of the errors. So in factor analysis diagrams, it's important to note that these numbers which you see up here at the top actually represent the variances of these given factors. So because there are no covariances between any of the factors, it's just going to be a diagonal matrix rather, where the diagonal elements are just going to represent the variances of these given errors. So it's going to be 0.64, 0.19, 0.51, and then the final element down here, if I could write it in, would actually be 0.36. So unsurprisingly, it's a 4x4 matrix, which matches the variance covariance matrix for our indicators, which we know is going to be a 4x4. So obviously what we could do is we could undertake this matrix multiplication here. We could either sort of do it manually, or we could feed it into some sort of matrix program like MATLAB, for example, and get it to do it for us. But there's actually a simpler way to use factor analysis diagrams to work out the model predictions of variances and covariances of given indicators. And I'm going to take you through it now. So suppose we want to work out the variance of the indicator y1, which in this example I've taken to be life expectancy. How might we work that out? Well, the way in which we do this is by doing a kind of walk where we start at the variable of interest and we end up with the variable with which we are ultimately interested in. So the variance of y1 is essentially the same thing as the covariance of y1 with itself. So this specifies the starting point and this the ending point. So what we do is we do a walk starting at life expectancy, going down to the factor which we first encounter, which in this case is physical health, and then we have to decide where to go based on the ending point, and the ending point is life expectancy, so we're just going to walk up again. So that green arrow specifies the kind of walk which we've done in our diagram. So how do we use that to help us work out the variance of y1? Well, when we walk down, we encounter a weight of 0.6, so simply we write down 0.6, and then we hit this physical factor, and because we don't then walk to any other factor, we then want to work out what is the covariance of that factor with itself. And because we're dealing with standardized factors here, that's just going to be 1. And then finally we walk back up to life expectancy, and we are going to encounter 0.6 again, so we get a final 0.6. One more thing, because we're talking about the variance of a given factor, now we also have to add the variance of its error term, which in this example is just going to be 0.64, which if you actually do the arithmetic here, it adds up to 1. And that's unsurprising because I've specified that we're dealing with standardized variables. Okay, so that wasn't too hard. How about if I wanted to work out the covariance of y1 with y2? So to do that, we just follow our exact same sort of technique which we used before. We're going to do a kind of walk which is starting where we want to start, which is at y1, and then ending at y2. So what we do is we walk down starting at life expectancy until we hit the factor, which in this case is physical health, and then we know that we need to walk up to BMI. So if we then use this, what we get is we first of all encounter 0.6 because that's what we encounter on our walk down, and then we hit this factor, but then we don't go to another factor, so we just want the covariance of that factor with itself, which in this case is just going to be 1, and then we walk up to BMI, which is then encountering an amount 0.9. And importantly here, because this variance covariance matrix of our errors is diagonal, we don't need to add any components onto this. Well, or strictly we need to add this component here in our error matrix, but because it's 0, we're just adding 0 on. So the model predicted covariance between these two indicators is just going to be 0.6 times 0.9, which is 0.54. Okay, so that was easy enough. How about a slightly more tricky one? So let's say we want to work out the covariance of indicator 2 with indicator 3. So we're trying to work out the covariance of BMI with how happy an individual feels. So in order to do this, we need to do a kind of walk where we start at BMI and we end at happy. So what we do is we start at BMI, we'll walk down to physical health, but then what we need to do is we need to traverse over to mental health and then walk up to happiness. And essentially what we need to do here is we're just going to write down all of the numbers which we encounter on the way. So the first number we encounter is this weight on this branch, which is 0.9. Then we want the covariance of physical health with mental health, because we're traversing between the two of them, which I don't know if you can see it here, but I've said it's 0.3. And then finally, we want to actually walk up this leg here, which has got a weight of 0.7. And because there is no covariance, which I'll specify between these errors here, then I don't need to add anything onto that. And if you do the arithmetic on this, it works out as 0.189. So I hope that that's provided a little bit of understanding as to how we can use factor analysis diagrams in order for us to derive the model predicted variances and covariances between indicators.